Question 3, it states, try to evaluate limit as x states, try to evaluate limit as x approaches 0 of fx with L'Hopital's rule, and using the cast to find derivatives of the numerator and denominator. What do you discover? And then it says how many applications of L'Hopital's rule are required. So we're going to use L'Hopital's rule to find a limit. So the solution to question 3. So if we take the limit as x approaches 0, we get the indeterminate form 0 over 0. For example, we just take the limit just to show you. Limit as x approaches 0 of sine of tan of x. Let's put this s a bit better. Of x minus tan of sine of x. Divide this by inverse sine of inverse tan of x minus inverse tan of x and sine, inverse tan of inverse sine of x, like that. And remember that every single one of these is approaching 0. If you look at the graph earlier, just to recall, every single one of these is approaching 0 there. It's all approaching 0 from either side for either inverse or regular function, sine or inverse sine or tan or inverse tan. So they're all approaching 0 as x is approaching 0. So what we're going to get is this goes to 0, then this goes to 0, so sine of 0. Tan of 0 is going to 0, and then the sine of that 0 is going to 0. So this goes to 0, this goes to 0, 0, 0, 0. And that means the outside is going to 0. So we get a 0 over 0, and this is indeterminate. Or 0 minus. Let's go complete. This goes to a 0 minus 0 over 0 minus 0, which goes to 0 over 0. And this is going to be indeterminate. Like that. So it's indeterminate, thus we can apply L'Hopital's rule, reference from my earlier video. So here's a link to it, there's video notes, archive, your screenshot from my calculus book, just because it's typed up. So L'Hopital's rule, suppose f and g are differentiable and g prime of x not equal to 0 on an open interval I. This is the derivative, g prime of x, that contains a except possibly at a, and suppose that limit as x approaches, as x approaches 0, as x approaches a of f of x equals to 0, and limit as x approaches a of g of x equals 0, or that we have the limits go to plus or minus infinity, or plus or minus infinity on the top or bottom. In other words, we have an indeterminate form of the type 0 over 0, or infinity over infinity. Then the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of the derivatives of f prime of x divided by g prime of x, if the limit on the right side exists or is infinity or negative infinity. And if if we also have a 0 over 0 on the limits, then we could keep doing that same derivative. Just keep applying L'Hopital's rule. And let's keep going further. So since the laboratory project asks us to use a cast to solve derivatives of the numerator and denominator, we could use the amazing Wolfram Alpha website. It's pretty epic. The first 6 derivatives all yield a limit of the indeterminate form 0 over 0. Finally, on the 7th application of L'Hopital's rule, we obtain non-zero values. So if you take the 7th derivative, you could just type 7th derivative of sine of sine tan of x minus tan sine of x. This is the numerator, sine tan minus tan sine at x equals 0, and it automatically solves it. So this is the 7th derivative, d over dx of 7, but they use this delta symbol, so partial derivative, but anyways, the same thing. It's only one variable. So this is going to be negative 168. And if you do the same thing for the denominator, so 7th derivative of a sine a tan of x minus a sine of x at x equals 0, we get the same thing. Derivative at this, you literally just write it and it will solve it. Negative 168. And we can just illustrate this here. So if we write first derivative of this one, zoom in, of the first derivative, and we just type just one derivative, or first, or or 1/10th derivative, it gets to 0. And if you go to second one, it gets to 0. Solve this one, it gets to 0. And there's some graphs that are pretty wild. And then you keep going 3. Let's go for reference just to show you. it's calculating, and it's 0. Go to 4, calculate and zoom in more, and it's 0. Let's calculate 5, and it's going to be 0. Let's see how the graphs look. Yeah, the graphs looks pretty cool there. The sixth derivative. Sixth derivative, it's going to be 0, and there's the graph, looks like that. And then seventh one, yeah, seventh one, negative 168, and there's the graph like that. Just fascinating stuff. So it goes to negative 168, and again, do the same thing for, yeah, this is the numerator. Do the exact same thing for denominator. There's a link, there's archive, and yeah, play around with it. You're going to get exactly the same thing. So negative 168. Thus the limit is, and we could take this limit as a limit as x approaches 0 of f of x. This equals to, this equals to, I'm going to write this as a limit just to make it save space. I'm going to write the numerator as a function, as x approaches 0 of n of x, for n for numerator, divided by d over d of x, which is the denominator. This equals to, and I'll put an h for L'Hopital's rule, and this equals to limit as x approaches 0 of, now it's going to be the nth, the seventh derivative. Put n of x, n7 like that in a bracket for the seventh derivative, and d7 for the seventh derivative of the bottom of x. So the limits equals to the limits, the limit of the n of x over d of x, which is, again, that's just f of x, is equal to the seventh derivative of the top and bottom. And this equals to negative 168 over negative 168, and this equals to 1. They all cancel. So the limit is equal to 1. Fascinating stuff. And yeah, so that's the answer. And also note that n of x and d of x are the numerator and denominator of f of x. And I'll just put this comma respectively, so it's in order. So numerator n of x and denominator d of x, like that.